Hello everyone, this is another video on atomic and molecular physics. Here we will be discussing nuclear, more numericals, right? So these are the gate previous year questions. PYQs, atomic and molecular physics. Right. So this is the first question. First question is in the presence of a weak magnetic field, weak magnetic field, atomic hydrogen atomic hydrogen undergoes the transition undergoes the transition what is the transition 2p half to 2s half, okay, by emission of radiation by emission of radiation number of number of distinct spectral lines, okay, that are observed in the resultant Zeeman spectrum, the resultant Zeeman spectrum, okay. In the presence of a weak magnetic field, atomic hydrogen undergoes the transition to p half to its half by emission of radiation. Number of different spectral lines that are observed in the resultant Zeeman spectrum. Right. So how to solve this question? See. So so here see. This is what is the transition given? 2p half to 2 is half. This is the transition, right? So if you remember, this is actually what this is called sodium D1 line. Sodium D1 line. Okay. So sodium D1 line, how many splitting will be there? So sodium D1 line has 4 Zeeman components only. Okay. Sodium D1 line has 4 Zeeman components. Total 4 Zeeman components only. Okay. This is what you have to remember. 2p half to 2s half, the sodium D1 line. Sodium D1 line has always 4 Zeeman components. Okay. Such an easy question. The answer will be 4. Right. Yeah. Next question. Question number 2. Question number 2. The spectral line corresponding to the transition spectral line corresponding to the transition. What is the transition? 2p half mj plus half to 2s half mj minus half, okay, is absorbed along the direction of is observed along the direction of the applied magnetic field. The applied magnetic field. Okay. When the emitted electromagnetic field is, then the emitted electromagnetic field is. Okay, this is the question. So the options are circularly polarized, circularly polarized. Option B, linearly polarized. Option C, unpolarized. Option B, not emitted along the magnetic field. So the spectral line corresponding to the transition 2p half mg is equal plus half to 2s half mg is equal minus half is observed along the direction of the applied magnetic field. Then the emitted electromagnetic field is what? Okay. So see how we solve this question. So the transition is what? 2p half mj plus half to 2s half mj minus half. So we have to check del mj. Okay. So del mj is how much? Plus 1. Because mine half minus minus half, that is 1. So del mj is equal to plus 1. And del mj plus 1 gives us what? It gives us sigma plus component. Okay. Sigma plus component. Which is what? Which is actually circularly polarized. Right? Sigma plus is your circularly polarized. Right? So see, this will be given mj values, because see j value is how much here? J value is half. So mj can have two values, minus half and plus half. How to get j values? 2j plus 1 values. So two values, minus half plus half. So plus half of 2p half is splitting into, transitioning into minus half of 2s half. So you have to check what mj is equal to how much. Half minus minus half, so that is 1. So if it is plus 1 from this side to this side, okay, plus 1, so this is sigma plus component, which is circularly polarized. All right. Yeah, this was a question number 2. Question number 3. Question number 3. Question number 3. The lifetime of an atomic state, lifetime of an atomic state is 1 nanosecond. Okay. So the natural line width natural line width of the spectral line of the spectral line natural line width of the spectral line in the emission spectrum emission spectrum of this state is of the order of lifetime of an atomic state is now 1 nanosecond. So lifetime is del t 1 nanosecond, that is 10 to the power minus 9 second. The natural line width of the spectral line in the emission spectrum of the state is of the order dash. Natural line width. Okay. So what we have to calculate exactly? So we know del E is equal to how much? H del nu, because E is equal to H nu. So del E is equal to H del nu. Okay. And del nu can I write as what? 1 by del T, isn't it? So H into 1 by del T, that is H by del T. Just put the value 6.625 in 10 to the minus 34 divided by 10 to the minus 9. Okay. 6.625 in 10 to the power minus 25. Okay. But here we have to calculate this thing in order of electron volt. Okay. So 5 10 to the minus 30 25 divided by 1.6 in 10 to the minus 19. Okay. So that will give me 4.14 into 10 to the minus 6 electron volt. Okay. So line width is what exactly? The energy, simply the energy. Okay. Natural line width of the spectral line. That means simply the what? Energy value. This is your what? Natural line width, which will be calculated in terms of electron volt. Okay. Which will be written in terms of electron volt. Okay. Yeah. That is the next question. Question number 4. Question number 4. The degeneracy of an these are gate PYQs. Okay. The degeneracy. See, it's not that hard. Questions are easy. Of an excited state. Degeneracy of an excited state of nitrogen atom of nitrogen atom. You also please write the questions, because while writing the question also this like question gets fixed in your mind. You only see the question and try to do, and sometimes questions gets skipped. Configuration. What is the configuration? 1s2, 2s2, 2p2, 3d1 is. So the delineation of an excited state of nitrogen atom having electron configuration. Excited state of nitrogen atom. Excited state of nitrogen atom. So see, this is the excited state that is given. 1s2, 2s2, 2p2, 3d1. We don't need the ground state, but how did it come? Nitrogen means 7, right? 7 means 1s2, 2s2. Just for understanding, 2p3. So what happened in the excited state? One electron from here went to the next state, that is 3d. Okay. So it becomes, this one has become 2p2 and 3d1. Right. So what is the question? Degeneracy of an excited state of nitrogen atom having electronic configuration this much. So what is the formula for degeneracy? Sorry. Formula for degeneracy. G is equal to how much? Is 2 whole into 12 plus 1. Okay. 2 into 2. What is 2L? L is what? L is the state in which the electron is there, the last electron. 3D. D means what? S, P, D, F. For L value is 0, 1, 2, 3. So L value is 2. 2 into 2 into 2 plus 1. That is, uh, that is, what happened? Okay. Anyway, 2 into 4 plus 1, that is 5, that is 10. So answer is what? 10. Alright. The answer is 10. Okay. So, so is what? Question number 4. Okay. That's question number 5. So, okay. Okay. Question number 5. Question number 5 is, when the ground statement, write down. Question is, the ground state of sodium atom, ground state of sodium atom 11 is how much? Is a 2s half state. Is a 2s half state. The difference in energy, the in energy, difference in energy levels arising, difference in energy levels arising in the presence of a uh, weak external magnetic field, weak external magnetic field, weak external magnetic field B. Okay, given in terms of given in terms of Bohr magneton, Bohr magneton mu B is how much? Okay, so ground state of sodium atom Na11 is a 2s half state. The difference in energy levels arising in the presence of a weak external magnetic field B, given in terms of Bohr magneton mu B is, ground state energy is given. Ground state energy is in a state of what? Is a state of 2s half. Okay, ground state. Now, difference in energy levels arising in presence of weak magnetic field. Okay. So how to do it? So Delhi we know. Delhi the formula is GMJ mu B. This is the formula for Delhi. Remember, Delhi is equal to GMJ mu B. So for 2s half, see here, J is how much? Half. So Mj is how much? Mj will have two values. Mj is half minus half. Okay, and yeah, that's it. I think so. Delhi for half is equal to, for Mj is equal to half is G into half mu BB. Delhi for this minus half is equal to how much? G into minus half mu BB. Okay, Delhi half. So the whole so okay, did I do this? Yeah. Oh, G value also. Yeah, G. G is a Landry factor. Landry factor, right? That will be 2. The value of Landry factor is 2. So this, just put the value 2 here. So if we put 2 here, 2 into half mu VB, answer is mu VB, and 2 into minus half into mu VB, the answer is minus mu VB, right? So the energy difference will be how much? Mu VB minus minus mu v is equal to 2 mu v. Delhi is equal to 2 mu v. Okay, that's the answer. 2 mu v. Okay, yeah, yeah. So this was your what? Question number 5. Okay, this was your question number 5. Question number 6. Let's go to question number 6. Question number 6 is the first Stokes line. The first Stokes line of a rotational Raman spectra. First Stokes line of a rotational Raman spectra is observed at what? 12.96 centimeter inverse. Okay, considering the rigid rotor approximation, the rotational constant is given by the rotational constant is given by how much? Okay. So first of all, what is Stokes line? What is Stokes line? This is your Raman spectra. This is the middle one is your Rayleigh line, isn't it? Excited line, Rayleigh line. This the right side is your anti-Stokes line, okay, and this one is your Stokes line. The difference between these two is 6b, 6b, but the afterwards it's 4b. Isn't it? It's like this in your Raman spectra, right? So first Stokes line. So this one, the first Stokes line is observed at 12.96 centimeter inverse. Considering the rotational constant is. So first outline is 6b, isn't it? 6b. Okay. See, this is 6b. So 6b is equal to what? 12.96 centimeter inverse. So b is equal to 12.96 divided by 6. That is 2.16 centimeter inverse. This is simple. This is your answer. This is your what? The rotational constant is b is your what? Rotational. See how easy it is. This is coming for 1 mark in GATE, NAT, NAT numerical answer type 1 mark. Okay, so don't leave these questions. Like this will give you a lot of marks in GATE. Okay, this was what? Question number 6. No? Question number 6 is over. Question number 7. Question number 7. Question number 7 is the term arising from the term J1 J2 arising from 2s1 3d1 electronic state in JJ coupling scheme. JJ coupling scheme R. Okay. There are 4 options. You have to okay. I won't give options. You have to write in terms of J1 and J2. Alright. So how will we write it? See. 2s1 3d1. JJ coupling means what? What should we do? What are the steps? First L1 S1 of first one and make the J like LS coupling of them, we will get J1. Exactly like L2, S2, J2. And then you have to do the J1, J2, that is J. Okay, that's what it is. So this is 2s1, 3d1. So L1 is how much? For S, L1 is 0. For S1, the half because it's electron spin half. L2 is for D, it's 2. And S2 is how much? Half. Okay, so J1 is how much? Half. J2 is how much? See, this is 3 by 2 and 5 by 2 because J is what? L minus S to L plus S. Okay. So now we will do what? This is half 3 by 2 and half 5 by 2. Okay. Half 3 by 2 will give me what values? Hmm? 1, 2. And this will give me what? 2, 3. That means half plus 3 by 2 and 2 half minus 3 by 2. That is 2 to 1. And this is your 2 by 2. That is 4 by 2. That is 2, 3. Yeah. Right. So this is how you have to rank it. Is it clear? We just did the JJ coupling this with this. Half 3 by 2 and half 3 by 2 they like mix up with each other to give 1, 2 and half 5 by 2. Okay. Next. Question number 7. Question number 8. Just a second. Question number 8. Question number 8 is the equilibrium vibration frequency for an oscillator is is observed at 29 cc. The ratio of the frequencies corresponding to the first and the fundamental spectral lines is 1.96. Considering the considering the oscillator to be anharmonic, the unharmonicity constant, the unharmonicity constant is okay. Equilibrium vibration frequency for an oscillator is observed at 2990 centimeters. The ratio of the frequencies corresponding to the the first and first and from this is I think this is first overtone. I think. Okay. First overtone and the fundamental spectral length is 1.96. Considering the oscillator to be anharmonic, the anharmonicity constant. Okay. So first overtone is how much? We know the formula first of all. Omega e chi e. Okay. So for first fundamental band. First fundamental band is how much? V0 to 1, right? So E0 is how much? Omega E by 2 minus omega E chi e by 4. E1 is equal to 3 by 2 omega E minus 9 by 4 omega e chi. Okay. So daily what? Daily is u1 minus e naught is equal to omega e minus 2 omega e chi. Now first overtone is what? First overtone is 0 to 2. E2 is how much? 5 by 2 omega e minus 25 by 4 omega e chi 0 to 2, that is 2 omega e minus 6 omega e chi. So the ratio of first overtone and fundamental lines is this one. So 2 omega e chi, so 2 omega e minus 6 omega e chi whole divided by omega e minus 2 omega e chi is equal to 1.96. Omega e is given. What is given? Equilibrium vibration frequency for an oscillator is observed at 2990. Equilibrium vibration frequency for an oscillator. So 29, so 29 much. So the equilibrium frequency. Right. So if you see, it's not even needed because see, I'll take omega e outside 2 minus 6 chi omega e outside 1 minus 2 chi is equal to 1.96, isn't it? So omega cancel out. So I just need to find out chi. I don't even need that 2990 centimeter inverse to it. Right. So 2 minus sorry 2 minus 6 chi is equal to 1.96 minus 1.96 into is 3.92 chi. So this is 2 minus 1.96 is equal to 6 minus 3.92 chi. 0.04 is equal to 2.08 chi e. So chi e is equal to 0.04 divided by 2.08, that is your 4 divided by 208. Okay, and if you calculate you will get it as 0.02. So this is your chi e is equal to 0.0. Okay, this is what anharmonicity constant. She's asking the question, isn't it? This is it. Okay. Okay, next is what? This is a question number how much? Question number 8. Question number 9. Question number Question number 9. Okay. Question number 9. In a normal Zeeman effect experiment, in a normal Zeeman effect experiment, okay, spectral splitting of the line at wavelength 643.8 nanometer, okay, corresponding to the to the transition 5 5.1 of cadmium atoms to be observed is to be observed. The spectrometer has a resolution of spectrometer has a resolution of has a resolution of 0.01 nanometer. Minimum magnetic field minimum magnetic field needed needed to observe this needed to observe this is right. So this is the question. Read the question again. Normal Zeeman-Effect experiment spectral splitting of the line at wavelength this corresponding to the transition of cadmium atoms is to be observed. Spectrometer has a resolution of this one. Minimum magnetic field is asked. Question is minimum magnetic field. Okay. First of all, separation of Zeeman components. Formula is separation of Zeeman components. Okay. Del nu is equal to EB by 4 pi m. Okay. Formula this formula EB by 4 pi m. Del lambda is equal to lambda square by C del nu. How did you get this? Because what del E is equal to h by lambda. Del E is h by lambda square into del lambda. So del lambda is what? Lambda square by C into what? Del E by h. Del E by h is what? Del E by h is del nu because E is equal to h nu. So del lambda is equal to h lambda square by C del nu lambda square by C EB by 4 pi m. Okay, this is del lambda. So from here we need minimum magnetic field. Magnetic field B is equal to what then? C by lambda square del lambda 4 pi m by okay. Just put the values. Put the values, we will get the answer. Right. Okay. This was your question number what? Question number 9. Question number 10. Okay. The spacing between vibration and energy levels in CO molecule is found to be 8.44 and 10 to the minus 2 electron volt. Reduced mass is given force constant. Okay. So if you see spacing, that is R is given how much? Um, 8.44. Sorry. Spacing between energy levels. Delhi is given 8.44 into 10 to the minus 2 electron volt. Reduced mass mu is equal to 1.14 into 10 to the minus 26 kg. Okay. Force constant K you are asked. Okay. You are asked what? K. Okay. So we know frequency what? Frequency nu is equal to 1 by 2 pi root over of K by mu, isn't it? If I just multiply h on both sides, h nu is equal to h by 2 pi. K by, this is E is equal to h by 2 pi. K by mu. So E is what? E is given. The separation of energy levels is given, isn't it? That is 8.44 10 to the minus 2 electron volts. We have to convert it into joules. Okay, is equal to H divided by 2 pi whole root over of K, which is needed, into divided by mu is given 1.14 into minus 26 kg. Okay, so from this we can calculate K. Right, force constant, that will be what? Newton per meter. So try calculate. Okay, so answer will be 186.7 Newton per meter. Right. Question number 11. The moment of inertia mi of a Mi of rigid diatomic molecule A is 6 times that of another rigid diatomic molecule B. Rotation energy of two molecules are equal. Rotation energy. Two molecules are equal. Mi is A is 6 times that of Mi of B. Okay. Corresponding values of rotational quantum number. So we know I is equal to what? Like it's equal to 0 to J plus 1. So, sorry, my bad. A is equal to what? X square by 2I. 0 to J plus 1. So we can see, so here EA is equal to EB in the question given. Right, rotation energies are equal. So if I equate them, x square by 2IA, JA whole into JA plus 1, and x square by 2IB, JB whole into JB plus 1. So if I take this IB by IA is equal to GB plus 1, IB by IA is 6IB, okay, GB, GB plus 1, J plus 1. And by 6 is equal to, so here the options are given, okay. From here you can check and tell me which option if I put, the answer will be coming like this. Option B, I think. Okay. We put this, right? So yeah, the option B is correct now. Okay, got it. Simple, again, simple question. Nothing much is there. Okay, so these are the questions up to gate 2014 we did. Okay. In the next session, we will be doing from gate 2015 to 2020. Okay, okay then. Till then, thank you. Okay, thank you for joining.